Okay, so first of all, we are asked to differentiate this function. I can't say anything about what you did. I simply didn't look. So obviously I have a function raised to a power. All I have to do is write f prime of x as 5 x to the 4th plus 3x squared minus 2 to the 4th power and multiply by, in parentheses, 4x cubed plus 6x. And that's it. You cannot do anything else, and you shouldn't even attempt. Is this okay? First one, okay, everyone? Any questions? Yes, Colby, go ahead.
I don't think it's a problem, but I put out an extra 2x and moved it to the front. Just to simplify the second part.
Oh, so you factor out the 2x.
Yeah.
That's awesome. That's fine. We can do that. So you wrote 10x then?
Yeah.
X to the 4th plus 3x squared minus 2 to the 4th power and multiplied by 2x squared and plus 3. Excellent. Good. Now for the second one. We have f prime of x. This is still the chain rule. We have to start with the outermost function. I shouldn't say we have, but that's what I recommend. Power 3. So this is 3. Sine squared of cosine e raised to 2x squared times. I have to differentiate sine of this argument, which is cosine of cosine e to 2x squared. So far, so good. So first I took care of the power, and I subtracted one from the power. Then I differentiated sine, which is this. Now I'm differentiating cosine, which is negative sine e to 2x squared. And now I'm finally inside e to 2x squared prime, which is e to 2x squared, times the inner function prime, which is 4x. So when we have a situation like this, I'm sure, and I hope you did not put any plus or minus, right? Everything is a product. So one more time, I differentiated the power, bring it down and subtract 1 from the power. Then I'd have to differentiate the inner function, which is sine, changes into cosine. Now I finally reached cosine of whatever, which is negative sine of that. And then finally I reached e to 2x squared, which e to a function prime is e to the function times the inner function prime. Yes, you can put 4x in front and maybe e to 2x squared, but there is nothing else. So this is 12x e to 2x squared, and then sine squared. I don't need this parenthesis. I'm going to take care of it. Sine squared of cosine and sine. And also I should put the minus in front to remove one set of parentheses. It's an additional set of parentheses. So I'm going to write minus in front, this minus, and then sine squared of cosine of e to 2x squared, and then times cosine of e to 2x squared, and then finally times sine of e to 2x squared. And that's final. Is that clear? Yes? Any questions? Okay, so now let's address the limit. And I think I saw that part I did see. I think everyone got that correctly, and I'm very happy. So yes, you could have used L'Hopital's rule here if you wanted to, because it's 0 over 0, but you don't have to. Okay, so all we have to remember is that when x approaches 2, this means x minus 2 approaches 0. So x approaches 2 or x minus 2 approaches 0 is the same thing. So I do have this piece here. I will factor the denominator, and that will give us exactly the x minus 2 as well as here. But I can't make a conclusion just yet because I see that 3 in front. So I have to be very careful. I will rewrite it as limit as x approaches 2. I know this is the same thing. X approaches 2 or x minus 2 approaches 0. Then the numerator has a 3. So this is the function. So I have sine 3x minus 2, and I need a 3 in the denominator times 2 times x minus 2, and I have to multiply top and bottom. So then this piece with this and with this, they will all be 1. Because x approaches 2, x minus 2 approaches 0, or 3 times x minus 2 approaches 0, they're all the same. But since I have inside here 3 plus, I have to have 3 times x minus 2, I have to have in the denominator 3 times x minus 2. And I saw in many of your solutions, I saw 3 halves. Of course, you can use L'Hopital's rule. Let's use L'Hopital's rule and see what we get. Because it's 0 over 0, of course. I should have said that from the beginning, or at least put it in. So when you plug in 2, you get 0 over 0. Sine 0 is 0. Okay, so if we apply L'Hopital's rule, then we will differentiate the numerator, which turns into cosine. I'm going to distribute because it's easier. 3x minus 6 times the inner function prime, which is 3. The denominator prime is 2. When x approaches 2, this approaches 0, but then cosine 0 approaches 1. And this is a very simple situation to get 3 halves in one step. This somehow, it's an algebraic manipulation. It takes a little bit longer, and you may see it or may not. But L'Hopital's rule is just one line. It's up to you, of course. Okay, I would like to continue. The plan for tonight is, we'll see if we can accomplish it, to show you more implicit differentiation, to talk about 3 inverse trig functions and their derivatives, and then move on to derivatives of log functions, and something called logarithmic differentiation. Okay, so let's continue with some examples with from section 3.5 implicit differentiation. You can choose, or I can choose. So we're still in 3.5. Anything from 5 to 20, including 25 through 32. I can choose, or you will choose.
15.
Which one?
15.
15 it is. Okay. So in 15 we have e to x over y equals x minus y. So this is number 15 on page 215. No one, by hand anyway, can solve this equation for y. So since I don't have y, and I am asked to find dy over dx, it's very clear that y is a function of, if I'm asked to find dy over dx, obviously I'm implicitly told that y is a function of, that's it. Good. So like before, we will differentiate the left-hand side and differentiate the right-hand side. Remember, y is a function, however. So when we differentiate the right-hand side, that's easy. Let's start with the right-hand side. How much is x prime?
1.
Minus the function prime. I don't have it, so I have to write this symbol that is the derivative of it. Now, careful with the left-hand side. Let me refresh your memory on the formula. E raised to a function prime is e to the function times? Exactly. So when I differentiate e to x over y, I will write e to x over y and times x over y prime. But x over y is a quotient. So I have to use the quotient rule, in which the denominator will be y squared. So now let's think about the numerator. When I differentiate the top function, I get 1 times the denominator, and then minus the top function times the denominator prime. But I don't have y. So then when I differentiate y, I just have to use the symbol again because I don't have the function. So as you see, it's a mess. Where is the variable? What are we looking for? Here's the variable. That's the variable that we want to solve for. But somehow I have to do some algebra to take that out of here, of the take dy over dx out of this mess. This is nice and clean, but this is not. So first of all, I'm going to separate the fraction into y over y squared and blah, blah, blah over y squared. That's my first step. Separate into two fractions. So let's do that first. So e to x over y over y squared will be 1 over y minus x over y squared dy over dx equals 1 minus dy over dx. Now let's see if this is clear so far. So the numerator has a difference of two quantities. So I put the first quantity over y squared and simplified it. And I put the second quantity over y squared and I have it here. Is this okay? Everyone? Yes? Okay. So now I'm closer. I will distribute this to 1 over y and this to x over y squared. So e to x over y minus x e to x over y squared dy over dx equals 1 minus dy over dx. I guess that's why this was in red in the book. Very interesting problem. And now it's up to you what you want to do. You can bring this over right here in front and this to the back, or the other way around. It doesn't matter to me. But we have to keep the variable, or the two terms that have the variable on one side, and the terms without the variable on the other. But it doesn't matter if you want dy over dx on the left and everything else without it to the right, or the other way around. So which one? Okay, so I'm going to move dy over dx in front. Minus x e to x over y squared dy over dx equals 1 minus this. Of course, the fraction line, the negative symbol, the equal symbol, everything has to be on one row, on the same line. Okay. Of course, I will factor out. What am I factoring out? And from which side? Since I cannot combine like terms, I will factor out dy over dx. Can anyone tell us what is left in parentheses on the left-hand side? Very good. X, yes, that's fine. Excellent. Yes. And finally, we have dy over dx. The numerator is and the denominator is. And no, I'm not going to do anything to it. I refuse. I'm on strike. Yes, I could. We can find the least common denominator, top and denominator, and try to simplify it a little bit. If you want us to do that, we can. If not, just leave it as it is. We don't have a point. We don't have anything to simplify here. But we could just simplify the expression a little bit. Is it a yes or a no? Okay. Okay. So dy over dx. The least common denominator in the numerator is y. So then this is y minus e to x over y. And the denominator is y squared. which is y squared minus xe to x over y. So then finally dy over dx. After I flip this and I simplify, I have a y left in the numerator. And that is fine. We know 6 trig functions and we know their derivatives. Yes? Yes? We know 6 derivatives for 6 trig functions. Of course, there are how many inverse trig functions? Also 6. However, I will not force you to remember just all 6, but just 3 of those. Arc sine x or sine inverse x mean the same thing. The derivative of arc sine x is 1 over the square root of 1 minus x squared. The derivative of arc cosine or cosine inverse is the same but with minus in front. And just one more. Which one is our favorite inverse trig function that we had in limits? We graphed it so many times. It's just our favorite.
Tangent.
Very good. Arc tangent x. Of course, this is prime. Sorry. Of course, I said it, but I didn't put it. It's 1 over 1 plus x squared. Of course, we have 3 more inverse trig functions. I'm happy with these 3. So the first 2 are easy to remember. One is positive, one is negative, and the rest is identical. And arctangent prime is 1 over 1 plus x squared. I would like us to choose a function and differentiate a function that has inverse trig, arcsine, arccosine, arctangent. So we see how this works. So we can move on to log functions. You can choose cotangent inverse, but I didn't show you the formula. So let's just stick with sine cosine if, which is not going to happen, but if I put something with the other 3 inverse functions, I will give you the formula. So the answer is no, I will not. I'm only interested in these 3. They're the most frequent ones. Which one? I'm sorry. Oh, Maria, I'm sorry. 50. This one. Okay, perfect. So we have tangent inverse of x squared, right? Yes. So 50. And that's on page 216. And the function is arc tangent x squared. We're asked to find f prime. We know that arctangent prime will be 1 over 1 plus what this is squared. But times, of course, times what? Times?
2 times the arctangent. Okay. Oh, no.
Right? Times the inner function prime. So if I only have x, I have 1 over 1 plus x squared. If you like, times x prime, but there is no need because it's 1. But if instead of x I have any other function, I have to multiply by its derivative. So then the simplified form will be 2x over 1 plus x to the 4th. Nothing changes from before. It's just that it's a new function that we are looking at. I think we should choose another.
58.
We want to choose 58, cosine inverse of sine inverse. Excellent. 58. Cosine inverse of sine inverse x. I think I read it correctly. Yes, cosine inverse of sine inverse. Excellent. Perfect. Okay, so now I have to determine f prime of x. And remember, I start from the outer and go towards the innermost. I have to differentiate. This is the argument. I don't care for it right now, but I need to differentiate cosine, arc cosine, or cosine inverse. And I know that this is negative in front, 1 over the square root of 1 minus, and now I will uncover this and square it. Okay, so this is sine inverse squared. Careful, sine inverse squared does not mean sine raised to -2. Be very careful. That's why most of the cases I prefer this notation instead of sine inverse. Okay, so one more time, here's what we did. We differentiated the outer function as -1 over the square root of 1 minus the inner function squared. But now times, I would have stopped here if this piece were just x, right? But I can't, it's a function. So now I have to multiply by the inner function prime. And when I differentiate arc sine, what do I get?
1 over
Exactly, the square root
square root of 1 minus
x squared. That's it. You don't have to do anything. You can't do anything here. So that's it. Very good pick. Thank you. Do you think we need another or we move on? Should we look at another function? Let me show you. Try to, when you differentiate, try to decompose the functions step by step, like I do. I use my prop. Don't you like my prop? Use a prop with your finger or something and say, okay, first I'm differentiating this and then I'm differentiating that. So you don't get lost because some of them are tedious. We want another or we move on.
59.
Which one?
59.
59. We just, 59. Very good. Yes, perfect. Good. On the same page, 216. And 59 is arc cosine. I prefer this notation for many reasons. It is not confusing, and also when I type, it's so much easier. I don't have to put a power. Yes, I guess I'm lazy. So typing arc cosine is much easier than typing cosine raised to -1 and then x, because I have to put in the equation editor. Perfect. So then y prime, or if you want dy over dx, which I prefer over y prime, arc cosine is -1 over the square root of 1 minus all this squared, b plus a cosine x over a plus b cosine x squared, which I'm not going to do anything to. Even if I square, let me see, if I square a plus b cosine squared and minus b plus a cosine squared, what is going to happen? Some terms will go away. Maybe we want to look at it and simplify it if possible. But let's continue because this is not enough. So remember, when I differentiate arc cosine, I get -1 over the square root of 1 minus blah squared. But since blah is not just plain x, now I have to multiply by the inner function prime. This is the inner function. But the inner function prime is a quotient, so I have to use the quotient rule. And the denominator has a plus b cosine x squared. Now carefully I have to differentiate the top, multiply by the denominator, minus the top times the denominator prime. So when I differentiate the numerator, what do I get? minus a sine x. So when I differentiate the numerator, b is a constant, 0. A cosine x prime is negative sine x, so I have negative a sine x, times the denominator, which is a plus b cosine x, minus. I copy the numerator now. You're not surprised, I ran out of room already. Okay, times. Now the denominator prime, which is negative b sine x, in parentheses, right here. Negative b sine x in parentheses. And moving forward, we have to vote whether we allow Thane to choose again. I'm kidding, of course. Okay, so let's leave this alone for a moment. I just try to simplify the second part. So I have negative 1 over the square root of 1 minus b plus a cosine x over a plus b cosine x, everything squared, times the denominator is a plus b cosine x squared. Let's see if we can do anything to the top. Okay. This times this is minus a squared sine x. This times this is minus ab sine x cosine x. This times this, so there, now this will be always positive because there is negative and negative in front, so positive b sine x times b, and then plus ab sine x cosine x. And no one understands what I'm doing here. Okay, should I write it again? It's not clear. Yeah, thank you, yeah. Okay, so forget about all this, this row, I'm gonna write it again, so negative 1 over, I'm just gonna put the square root here and you know what I mean, so I have enough room for the rest. So a plus b cosine x squared. So negative a squared sine x minus ab sine x cosine x plus b squared sine x plus ab. There's no way I can fit this in. But look at what happens here. These two go away. Negative ab sine x cosine x with positive ab sine x cosine x, they go away. And now I have negative a squared sine x plus b squared sine x. Since we decided to simplify, I would have personally left it alone. I'm going to try and see what happens here under the square root. So 1 minus b plus a cosine x over a plus b cosine x. Since we chose this, now I'm curious to see if I can simplify the quantity under the square root. Okay, so this is 1 minus b squared plus 2ab cosine x plus a squared cosine x over the denominator x squared plus 2ab cosine x plus b squared cosine, of course, cosine squared. Okay, so I'm trying to find the least common denominator and see if I can simplify. So the denominator is still, and now I can go back and just write it as is, because I just wanted to see it. So I don't really need to expand the denominator. We never do that. I needed to expand it to try to simplify it, but I'd rather have it in the factored form. So then this becomes a squared plus 2ab cosine x plus b squared cosine squared, but then minus all the other terms. Minus b squared minus 2ab cosine x and minus x squared cosine squared. Yes, I knew that those two will go away. I can factor out, I can do this, and then minus cosine squared x and a squared minus, yes, a squared minus b squared over a plus b, I jumped, cosine x squared. Okay, so I will factor out, yes, I can simplify it, and it simplifies quite nicely, actually. I see what happens here. So the numerator, I factor out a squared minus b squared from these two. All this work is just for that denominator, that fraction, 1 over the square root. So I factor out a squared minus b squared. Then I get 1 minus cosine squared, which is sine squared, over a plus b cosine x squared. And when I apply the square root from this, I will get the square root of a squared minus b squared sine x over a plus b cosine x. Now, I don't know if this would make any difference with the rest. Now I have to go back and take a look at what the rest is having there. So yes, one factor in the denominator will go away. That's really not warranted because we're not really looking at anything else after this, but since I started, now I'm going to finish it up. So it's -1. So now the square root in the denominator is basically this, and I have to flip it. So it's a plus b cosine x over the square root of a squared minus b squared times sine x. This is all this. And now I will factor out, so this is times, I will factor out negative sine x, and this is a squared minus b squared, and the denominator is a plus b cosine x squared. So yes, after 3 pages of work, it does simplify. And you can say, who cares? I agree. So 1 from here, a sign from here with a sign from here. So the negative with the negative. So this is a squared minus b squared. Everything over the square root of a squared minus b squared sine x, a plus b cosine x. And we prefer the square root to be at the very end. So I'm going to remove it from the beginning. You can rationalize if you want as a final step. And if you do rationalize, you will eliminate a squared minus b squared from the denominator. So we multiply and divide by it. So this becomes finally, and this is it. But yes, it was just algebraic manipulation after algebraic manipulation, and it's not such a big deal. But it was an interesting problem. Mason, I'm glad you're here, so if you have any questions, I can stop and look at your questions.
I watched the lecture videos too for this class, but
okay, very good. Okay, so moving on to 3.6, the derivatives of log functions. So we start with, of course, with f of x equals natural log x. F prime of x for this particular function is 1 over x. Also, for something that we will be using in chapter 5, I would like to look at natural log of the absolute value of x. Obviously, natural log of the absolute value of x has two possibilities. Why? Because the absolute value has two possibilities, and we know that. So can anyone tell us how to simplify this function before we talk about, and you will see later why I need this. So we have to talk about the absolute value first. And we know that absolute value has two options. Because the absolute value has two options, natural log of the absolute value would have two options. And therefore, you see what happens with the derivative of natural log of the absolute value. So what are the options for the absolute value of x?
X and negative x.
Very good. For x greater than or equal to 0 and for x less than 0. However, as you know, I cannot plug in 0 in natural log. So I still have two options for the absolute value, for natural log of the absolute value, but only when x is strictly greater than and x is strictly less than. I cannot put 0 in there. Natural log has a vertical asymptote at 0. Okay, so then what are the options then for this function, for natural log? The absolute value, the natural log of the absolute value.
Just
Very good. So now I would like to differentiate this function. We just learned that natural log prime is 1 over x. So what will be the derivative of this? Perfect. But now this is a function, right? So if natural log x prime is 1 over x, if I have natural log of a function prime, this cannot be just 1 over f, but it has to be times f prime. Good. So now this is not plain x. It's a function. It's negative x. So then, when I differentiate natural log of negative x, I have 1 over negative x, but times the inner function prime, which is negative 1. But what is this? Exactly. It is the same. So therefore, we will write the natural log of the absolute value of x prime is 1 over x. Of course, when x is not 0. Why is this important? It is extremely important for chapter 5. Because in chapter 5, I'll explain why and why we're doing this and what techniques we're using, etc., when we get there. But in chapter 5, we're going to go backwards. So we are going to integrate 1 over x dx. Don't even write this. This is not for now. And the answer has to be natural log of the absolute value of x plus a constant c. So this is for later, much later. That's the reason why we have to remember that when we differentiate natural log of the absolute value, we get 1 over x. Okay? So don't write this. This is for later. Okay, I would like to practice these formulas and then talk about a major topic, which is logarithmic differentiation. Very important topic. Okay, so derivatives of log functions. We are on page 223. Please choose anything you want. So I recommend that if you allow me something like, I did not show you yet what is the how we differentiate a log in any other base. I only showed you how to differentiate natural log. So something like this, so we don't know that yet. In a minute, I'll explain. So this, something like this, something like this, something like this, any of these with natural log. And then I'll explain how we get the derivative of any other log meaning in other bases, but e. And then we'll talk about logarithmic differentiation and why it's needed. Would you like to start with 12 and then you can pick another? Okay, so 12 and then pick another, please.
16.
You want 16? Okay. So we want to look at 12 and then 16. Perfect. So 12, page 223, is h of x, natural log x plus the square root of x squared minus 1. Okay, so I see a natural log of a function. Again, I imagine that that is not there, so for now. So I have h prime, which is obviously 1 over whatever that is. Natural log of a function prime is 1 over the function. Let's see. So it's x plus the square root of x squared minus 1. But since this is not plain x, I have to multiply by the derivative of that function. Is this okay? Are you with me? Yes? Okay, perfect. So now, can anyone differentiate x plus the square root of x squared minus 1? Yes?
1 plus times 2x.
Excellent. Any questions? Okay, let's try again a little bit of simplification. Maybe it's possible. I will simplify 2 with 2. So this is 1 over x plus the square root of x squared minus 1 times. What is the least common denominator in parentheses? And there is only 1. Very good, the square root of x squared minus 1. So, of course, this one gets an x squared minus 1 and plus x. This is quite nice. Have we noticed anything already? Excellent. So how nice this is, indeed. And that's it. Very good. So when we found the least common denominator, I changed this into the square root of x squared minus 1 over the square root of x squared minus 1 to add those two fractions. So that's this one changed into the square root of x squared minus 1 and then plus 1 times x. Is that better? Yes. Okay. We also picked 16. Any questions on the previous problem? I think it's t cubed. Yes, it is. Okay, so what do we know about differentiating? Natural log of the absolute value, or dy over dt in this case. So remember the formula? The derivative of natural log of an absolute value of a function, it could be a function, and then it's 1 over the function times the function prime. So we have 1 over 1 plus t minus t cubed and times
3t squared.
1
Oh, the t.
minus 3t squared. Good. Okay, so I know I have about 15 minutes. It's sufficient to explain what logarithmic differentiation is and why is it so important. logarithmic differentiation. And I'm going to pick a problem like 48, which is y equals sine x, and sine x is raised to power natural log x. And after that, if I have time, I would like to show you how to differentiate a log in any other base but natural log, but base e. Okay. Ready? We're asked to differentiate this function. What do I need to do? What rule do I apply? Let me save you some time. No rule exists for differentiating of a function raised to another function. A function raised to a power like 5, 10, 11, negative 3, yes. But a function raised to another function, there is absolutely no rule. But there is a way. We will apply natural log to both sides. Let me refresh your memory on one of the properties of log, which is the power rule. So if we have natural log, let's say, of a raised to x, we know that the power goes in front as a factor, and we multiply by natural log a. And that's exactly the property we're going to use now. So this is basically an equation. The left-hand side equals the right-hand side. I applied natural log here, and I have to apply natural log to the other side. So therefore, I will bring the power in front of natural log. It happens to be natural log, but it's a power that I bring in front as a factor. So now the new equation is natural log y equals natural log x multiplied by natural log of sine x. So what have I accomplished so far? You could say nothing, and I would kind of agree. I didn't accomplish. I didn't find the y prime yet. What do you think I'm going to do next? It's our second best friend from last week. What is our first best friend is the square root. We know that. Our second best friend is implicit differentiation. That's our second best friend. The left-hand side now is something we just learned today. How do I differentiate natural log of a function? 1 over the function times, yes, but I have to write it as dy over dx. I don't have to, but please write it as dy over dx. Okay, on the other side now, we have to notice that this is the product rule, because we have a function which is natural log x multiplied by another function which is natural log of blah, blah, blah. So the product rule always requires us to write a sum of 2 terms. I differentiate the first function. What do I get? Perfect. Times the second function, leave it alone. Plus the first function, natural log x. But now I have to differentiate the second function. But now I have natural log of a function to differentiate. How do I write this?
So aren't you going to use the chain?
Yes.
Oh, wait, no, you take, so it'd be 1 over ln sine x.
No. So natural log of something is prime is 1 over sine times, exactly, thank you, times cosine, the inner function prime. Okay, I'm going to write this one more time to make it more concise, clean it up a little bit. So I have 1 over y dy over dx equals natural log of sine x over x plus natural log, and allow me to write this as a cotangent because it's cosine over sine. Okay, now I'm solving for this. That's my variable. That's what I'm trying to determine. So then I have dy over dx equals what? What should I do to both sides to find the derivative of this function? I don't want 1 over y times dy over dx. I just want dy over dx by itself. What should I do to both sides to get rid of 1 over y? Multiply by y. Instead of multiplying by y, I know the function is sine raised to natural log. I'm going to multiply by sine raised to natural log. I would not touch any of this. I will just use brackets and put them and write them again, and that's it. A lot of work. This is not a trivial problem. So let's review the steps and then choose another problem. I realized that this was a function raised to a function, and there is no differentiation rule for something like that. My only hope was to bring one of the functions down, and the only function that does that, if I apply it to both sides, is natural log, or log, but natural log is the easiest. So that applying a log to both sides allowed me to use the property of log that brings the power in front as a factor. Now I no longer have a power, I have a product, which is easier to handle. And on the other side I have a natural log of the function. And then we applied implicit differentiation and we got to this stage. I had to get rid of this, multiply both sides by y, but I don't want to write y. This is the function, sine x raised to natural log x, and then I just copy the rest. So this is the expression that gives a derivative of sine raised to natural log. Okay. Yes, please.
So what if you had like ln
Yes.
a
So you mean log base a?
Yeah.
Yes.
Times x.
Of x.
Yeah.
So this is f of x. Yes, that's exactly what I was telling you. I wanted to choose another example.
Oh.
And then, no. It's better to do this now. Since you asked, it's better. Okay. So remember there is what is called the change of base formula. So this log has base a, which can be easily changed into natural log x over natural log a. So when we differentiate log in any base, we are really differentiating this. It's 1 over x natural log a. So log base a of x prime is 1 over x natural log a. Because 1 over natural log a is just a constant, it stays outside, and when I differentiate natural log, I have 1 over x.
So in theory, could you do it reversed? Like, say you only had 1 over x ln a.
So I want to differentiate this, then I will find the second derivative of that.
Okay.
Right, if I differentiate this, because this is the derivative of log base a of x. If I want to differentiate it again, then I will have the second derivative of log base a of x.
Okay.
Better? Okay. So we have time for one more, maybe two. So let's choose. These are problems 39 through 50. Extremely important technique. So I misspoke. So mainly 43 through 50. These have absolutely no rule. They cannot be determined. We just looked at 48, sine x raised to natural log x. Let's choose another. They're all identical. But we need to practice at least one more.
We do 49.
49, the tangent raised to 1 over x. Excellent. So 49, y equals tangent raised to 1 over x. I have a function raised to another function. There is nothing I can do. I have to apply log to both sides. I have to apply log because I need this mechanism that only, or property that only log has to bring the power in front as a factor. There is no other function that does that. Okay.